Hey guys, today we're going to be looking at radiation and nuclear equations. So in this video, by the end of it, you should be able to know the different products of nuclear reactions. You should be able to relate their energies, ionization potentials, and penetrating ability, and write some general nuclear equations. So let's go over some terms real quick. First is the idea of a nuclide, which is a distinct kind of atom or nucleus. Characterized by a specific number of protons and neutrons. Okay, it is the basis for an isotope, where an isotope is a set of nuclides. That have the same number of protons. But different numbers of neutrons. And then within here we can have a radionuclide. Okay, so this is a nuclide that's unstable, radioactive. And because it is radioactive and it is because it's unstable and radioactive, it's going to decay. Into a different stable nuclide. And it'll keep decaying until it gets to that nuclide. And then we have something called a nucleon. And this is either a proton or a neutron. It's something within the nucleus. So it can't be an electron because that's not within the nucleus. So in this chapter, in this section, we're going to be talking about nuclear energy, and it's very different from chemical energy. When we have chemical energy, it's breaking and making of bonds. Nothing's happening to our nuclei. Nuclear energy, on the other hand, we are changing our nucleuses. So nuclear energy comes from the changing of one nucleus into another. So our nucleus is breaking apart or it's getting fused together, but something's happening to the nucleus itself and it is changing. And because of that, the energy of a nuclear reaction is enormous in comparison. So it's much more significant amounts of energy when we're talking about changing an atom into another atom. And nuclear energy, if we talk about a nuclear power plant, we're talking about nuclear energy, and it accounts for about 13% of the energy worldwide. And it depends on what area we're talking about. Here's just a couple of different areas. So United States, France, and China. France has the greatest amount of nuclear energy, while China has the greatest amount of coal energy, the least amount of nuclear energy. So when we're talking about the nucleus, We have two different types of nucleons, our protons and our neutrons. So our nucleus has nucleons. And unlike chemical reactions where we care about the electrons, we don't really care about the electrons in here. We're not really looking at it. We're looking at our protons and our neutrons. Remember that our protons give us our atomic number, and different neutrons give us different isotopes. Okay, so anytime we have an isotope of an element, they're going to have the same number of protons, but different number of neutrons. And some isotopes, radioisotopes, are going to be radioactive species. So a radioactive isotope called a radioisotope is an unstable isotope, so all of the atoms within the isotope are unstable. And because of this, it's going to spontaneously emit high energy particles and radiation, or high energy particles and electromagnetic radiation. And these are going to be ionizing, in that they have the ability to cause an atom to lose an electron. Here are examples of our electromagnetic radiation. So this is our electromagnetic spectrum, and it goes from extremely low amounts of energy to extremely high amounts of energy. Our non-ionizing energy, our non-ionizing radiation, will not cause the ejection of electrons upon exposure to it. And then our ionizing radiation will, and that includes stuff like gamma rays, right here, which are ionizing radiation and radiation that is emitted from an unstable nucleus. So what's going on within an unstable nucleus? When we're thinking about an unstable nucleus, it's due to a imbalance within the nucleus itself. So two forces are going to exist within a nucleus. We have the strong nuclear force, and there's also a weak nuclear force, but we're not going to look at that. And then there's also the electric force. The strong nuclear force is an attractive force. It's what holds the whole nucleus together. So it holds our nucleons together. And it is very, very strong. But unfortunately, it is very short-lived, so it's got a very short distance. Okay, so by very strong, I mean it is 1 times 10 to the 38 times stronger than the gravitational force. So it is incredibly strong. Our electric force is what causes repulsion within our nucleus. And it's between the like-charged protons. So it's proton-proton repulsions. Okay? And this is going to be weaker but longer range. So when we think about the two forces, we can see them both right here. So our nucleons are all being held together by the strong nuclear force. And it's generally the force that's kind of emanating from our neutrons themselves is usually what we think about. And then the protons are going to repel other protons. Proton-neutron, very strong nuclear force between them. Proton-proton, weak but repulsive force between them. And what happens as we are at smaller nuclei, no big deal. Our strong attractive force is so significant that it can outweigh the repulsive electric force that the protons are feeling. However, when you start to get larger and larger, what happens is you start to have the strong nuclear force outweighed by the repulsive electric force, because now our nucleons are further and further apart. So this nucleon can no longer attract this nucleon, but this proton can repel this proton. So it's just a balance between those attractive and repulsive forces, and the balance just is not quite right as we get to large enough nuclei. So for smaller nuclei, the forces balance out. And we have a stable nucleus. Large nuclei, the nuclear charge is not long range enough to counteract the repulsive electric force, unstable nuclei. And what we find is if we're large enough, so atomic number 84 and greater, no longer stable. We can see this when we look at this radioactive table of the elements. Anything that's been colored in with black, the only isotopes that are available are radioactive isotopes. And if we look at these, we can see that once we hit 84, we do not have any that are going to have a stable isotope available. They're all going to be radioactive because we're so massive at this point that the electric charge is just ripping the nucleus apart. Technetium is the only real weird one. It's fairly low weight, but despite that, it's only got a radioactive isotope available. And then promethium is also a little bit weird because it also only has a radioactive isotope available to it, despite the fact it's the only lanthanide that's like that. Generally, you're just talking about high molecular weight substances when you're thinking about this. Uranium, that's what they use in nuclear power plants. So a couple of these should sound familiar, but all of them are going to be radioactive. So no stable nuclei, and it's all because they have such massive sizes. And I also want you guys to look at the proton to neutron ratios. And for like helium or lithium, those are kind of close to a 1-to-1 ratio of protons to neutrons. But if we look at something like ytterbium, ytterbium has 70 protons and the atomic mass is 173. So that means it has 103 neutrons. So a significantly larger number of neutrons versus protons. And it's to try and hold everything together as we kind of consider our neutrons to be our nuclear glue. When we have a radioactive decay process, an unstable nucleus is emitting radiation. We have three forms of radiation that we look at: alpha particles, beta particles, and gamma rays. Those are the most common, but we're also going to look at a couple of other emission products or radioactive decay products, including the positron and electron capture. So I want to go through all of the different types of radioactive decay that your book shows. Okay, so when we have a nuclear equation, we have to balance that nuclear equation. And it's unlike balancing chemical equations. With chemical equations, you add a coefficient to say how many of each type of your atoms or molecules or compounds that you have. Here, you're looking at your sum of your mass numbers versus your sum of your atomic numbers. So make sure that the sum of the atomic numbers and the sum of the mass numbers on both sides of the equation are equal. And that's going to be the easiest way to solve for these radioactive decay equations. So let's first look at alpha emission. Alpha, an alpha particle, is a slow-moving, high-energy particle. And it is a helium nucleus. It has a atomic number of 2. It has a mass number of 4, so it has 2 neutrons as well. So we write it like this. So this is our alpha particle. It has no electrons, but it does have a +2 charge. Okay, and because it's fairly massive, and it has a large charge, it's going to be the most ionizing. So it has a very high ionizing potential. But because it is so large and is so slow, it has a low penetration depth. So generally, we would not consider alpha particles to be that dangerous as long as you don't open your mouth. So this would be stopped by a piece of paper. Okay, so this is how we write a alpha particle. So when we're thinking about how we're going to incorporate this into an equation, we have 238 uranium, like this. This is our mass number. This is our atomic number. And what's going to happen is it's going to emit that alpha particle, like so. So we need to take 238 minus 4, which gives us 234. And then we need to take 92 minus 2, which gives us 90. And this is going to be the mass number and the atomic number for our new species, 234 over 90. And if we look on our periodic table, 90 is thorium, like so, as we see right over here. Okay, so it's as simple as that. If I say, okay, uranium emits by alpha decay, you're going to write uranium on the left side. You're going to write an alpha particle on. You're going to write uranium on the left side. You're going to write an alpha particle on the right side, and then you're going to subtract the mass number and atomic number from uranium to get 234 thorium. But uranium is not the only thing that will undergo alpha emission, so you will have to do some balancing with other species. Next, we have our beta particle, or beta emission. So a beta particle is a high energy electron. As such, it's going to have a -1 charge, but no real mass, but not much mass. Okay. We generally write a beta particle either as a B with a 0 and a -1, or as a E with a 0 and a -1. So either one is how we'd write a beta particle. And then when we're talking about beta particle emission, what's going to happen is nothing's going to happen to our mass number, but our atomic number is going to go up by 1. So our atomic number of the product will go up by 1. So we can see that here, going from carbon 14 to nitrogen 14. So that's like what's going on. So we've got carbon, and as it ejects that electron, nothing happens to our atomic number. But over on this side, we have 6. Over on this side, we have -1. So we have to have 7 in order to get 6 on that side. So we're going to go up by 1, giving us nitrogen. We generally consider beta emission. What's actually occurring is a proton is being formed by the decay of a neutron. So in beta emission, a neutron decays to produce a proton, which attaches, and an electron, which is ejected. And that's our beta particle, right? And then this attaches to there. So we have 1 fewer neutron, 1 additional proton. So it's beta emission is also a neutron decay. Next is our gamma emission. Gamma particles, or sorry, gamma rays are electromagnetic radiation, high energy electromagnetic radiation. And as such, it has no charge, no mass. But it's going to have the greatest penetration depth and lowest ionization potential because it has no charge and no mass. Greatest penetration because it interacts with matter the least. And because it has the greatest penetration depth of the 3 forms we're talking about, the alpha particle, the beta particle, and the gamma ray, it's going to generally be considered the most dangerous. But it does have the lowest ionization potential because it doesn't have any charge. And then, of course, beta particle is going to be in the middle. It's going to have a greater penetration depth than an alpha particle, but it's going to have a lower ionization potential versus the alpha particle, and then less penetration depth versus a gamma ray, higher ionization potential versus a gamma ray. Okay, so generally gamma emission accompanies another nuclear decay process. So what you're going to have is you're going to have a metastable state, and then after that metastable state, you emit that gamma ray, and then it goes to a stable state in theory. So the metastable state emits a gamma ray, and then it gets to a stable state. And if you're just writing the gamma ray, it is written like this, or you can put 0, 0, as just the emission of a gamma ray will not change anything about your atomic number or mass number. So technetium, metastable technetium would look like this. And then it would emit a gamma ray, and it would go to not a really stable technetium, but a more stable state. Next thing we're going to look at is positron emission. So positron emission is, a positron is basically a positive electron or positive beta particle. So it's going to act exactly like a beta particle, except for now we have a +1 charge versus a -1 charge. So instead of increasing our number of protons, we're going to increase our number of neutrons, decrease our number of protons. So the idea with the positron is a proton decays, forming an electron and a neutron. So we're going to decrease number of protons and increase number of neutrons in our product. Okay. So if we have carbon 11, taking that 11, nothing happens to it, but our 6, we're going to have a +1 here. So we have to have a 5 here. So we're going to our positron plus boron in this case. And again, this is a proton decays to produce a neutron plus a positron. Okay. Last one we're going to look at is electron capture. Electron capture is exactly that. You're capturing an electron. So this is, instead of an emission of a beta particle, this is the absorption of a beta particle. For instance, we could have rubium 81, and it could capture an electron. What happens is one of those protons is going to combine with the electron to produce a neutron. So we're going to go to krypton 81. So our atomic number goes down by 1, and our mass number doesn't change. Okay, and that is everything for this video. I'll talk to you guys in the next one.